friends, welcome to Veteach classes. So now let us discuss about classification of fluids. So if we see here, the first fluid is ideal fluid. What is ideal fluid? A fluid which is incompressible and having no viscosity. Such a fluid is known as a ideal fluid. But really ideal fluid will not exist in practical. So for analysis purpose, we assume that ideal fluid will exist. Next is real fluid. So what is real fluid? Real fluid which possesses some viscosity is known as real fluid. All the fluids which are existing in nature are real fluids only. Next, Newtonian fluid. Newtonian fluid means it is a real fluid which obey rate of shear stress is proportional to shear strain. Newtonian, if a fluid that obey that law is known as a Newtonian fluid. Let us see a real fluid in which the shear stress is directly proportional to the rate of shear strain or velocity gradient. So velocity gradient means du by dy. Okay. Next, non-Newtonian fluid. So non-Newtonian fluid means here the rate of shear stress is not proportional to the rate of shear strain. Then how it will be? So for non-Newtonian fluids, the shear stress varying will be like this. So tau is equal to A into du by dy power n minus 1 plus b. So this is the equation for Newtonian fluids. Let us see it in detail. So the first type of Newtonian fluid is dialant fluid, or we also name it as shear thickening fluid. If you see the graph, the dialant fluid is passing through the origin. That means for dialant fluids, B is equal to 0, and it also having an increasing slope. That is here n is greater than 1. So this is the condition for dialant fluids. So for dialant fluids, the apparent viscosity increases with rate of deformation. That means let us write the equation as tau is equal to A into du by dy power n. Okay. So into here for fluids, the apparent viscosity increases with rate of deformation. But for pseudoplastic fluids, which is having the value as B is equal to 0 and n will be less than 1, as we can easily see that the slope is a downward curve for shear thinning fluids. So here the apparent viscosity U apparent is decreases with the rate of shear strain. So this fluid is known as shear thickening fluids. The best example of shear thickening fluids is solids with solution with suspended stalk, and the best example for shear thinning fluids is paint, right? Next is ideal Bingham plastic fluid. So here the graph for ideal Bingham plastic exists here. So this represents for deformation of that fluid, we have to apply this much of shear stress, then only the deformation will takes place. And this graph is with respect to x axis we have du by dy, and on y axis we have shear stress. And the graph, that means if the straight line is coinciding with x axis, we name it as ideal fluid, and that means whenever the graph is on x axis, the line is on x axis, what that represents, even though there is deformation, the stress is 0. So the opposite for that is line that will coincide with y axis. Next is what is adhesion and cohesion. If you see, cohesion is the force of attraction for between the adjacent layers. They are attracting, that is known as cohesion. And adhesion is, it represents the adhering or clinging ability of the fluid molecules. That is, if the force of attraction between the molecules is opposite to each other, then it is known as adhesion. Okay. The next is wetting and non-wetting surface. If you see here, wetting surface means that will be having an angle theta less than 90 with respect to the adjacent layer. For non-wetting, the angle will be greater than 90. So we will consider the water as a wetting liquid and mercury as a non-wetting liquid. Next is surface tension. So what is surface tension? For example, take a beaker with water. So let us take molecules inside it. So let us take the example here. So here the molecule A is having forces in everywhere, right? So it is in equilibrium condition. That is, the net force is 0. If you see molecule B is also in equilibrium, because everywhere the molecule B is attracting surrounding molecules, and all the net attraction force on the molecule B is 0. But if we had seen for molecule C, there is no liquid layer on this side of the C, that is top side. So there is top side is free surface. There are only molecules on bottom side of C. point C. So the molecule C will attract the nearby molecules with respect to water which are lying on the bottom side. So there is no molecule or there is no force on the top side. So there is a resultant force on the molecule B that is acting in downward direction. If you see here, for but molecule C which is situated on the free surface of liquid does experience a resultant downward force. Yes, therefore there is a net attractive force acting on the molecule at the surface of the liquid, that is your molecule C, which tends to pull the molecule on the surface towards the interior of the liquid. The force is balanced by a repulsive force, as the net force is net force on the molecule C is downward, the repulsive force will be upward. So every molecule near the layer will act some repulsive force like this, and this repulsive force for unit length is known as surface tension. So surface tension is denoted with symbol sigma, and it is having units of Newton per meter, and surface tension is due to the cohesive property of the liquid. Let us see the surface tension for a liquid droplet. So this is my liquid droplet. So let us consider sigma be the surface tension of the liquid and P be the pressure intensity inside the droplet, and D is the diameter of the droplet. Let us cut the droplet into two halves. So if I take this droplet and if I cut into two parts, so this is how my molecule looks like. So if you see the tensile force due to surface tension acting on the circumference of the portion, so as we have seen, this arrow mark represents the sigma, nothing but surface tension, right? So what is the tensile force? So tensile force means on which area it is acting. It is acting on the entire circumference, so sigma into circumference, that is the tensile force. And what is the pressure force? If you see, the pressure is acting inside this area, so to find pressure, force is equal to pressure into area. So the force produced by this pressure is P into pi by 4 d square. So as we assume equilibrium condition, we will equate pressure force to the surface tension force. So P into pi by 4 d square is equal to sigma into pi d. So if you solve for P, we will get 4 sigma by d. So this is the surface tension for a liquid droplet. So from this we can write surface tension sigma is equal to P into d by 4. Surface tension on hollow bubble. So for hollow bubble there will be two types of layers, that is outer layer and inner layer. So we will get 2 into sigma of pi d, and my pressure acting on the inner surface will remain same, but the surface tension will act on two layers, that is we will have a layer like this, inner diameter layer and outer layer. So the surface tension on inner layer looks like this, and the surface tension on outer layer looks like this. So what will happen here? It is sigma and here also sigma. So the surface tension force is, for inner layer it is sigma into pi d, plus for outer layer also sigma into pi d. So if we add, we will get 2 sigma pi d. So if I solve for P, I will get P as 8 sigma d, 8 sigma by d, where sigma surface tension can be written as Pd by 8. So it is half of the surface tension produced in a liquid droplet. Next, surface tension on a liquid jet. So if we see, we have a liquid jet of having length L and diameter d. Let P be the pressure inside the liquid jet and d is the diameter of the jet. Then we have to equate the surface tension force with the pressure force. So here the surface tension is acting on the two edges of this liquid jet. So here the surface tension force is sigma into L on one side, on this side, plus sigma into L on this side. So it will be 2 sigma L. Fine. Next, what is the pressure? So pressure is acting on this area. So if you project this area, it looks like this, and the projection of this cylindrical liquid jet is, it is having a length L and diameter d. So its area will be L into d. So here if we take pressure force is pressure into area L into d, which is equated to surface tension into twice the length, that is the surface tension force 2 sigma L. So we will get P is equal to 2 sigma by d. From that we can write surface tension is equal to Pd by 2. Okay, fine. Let us discuss what is capillarity. So capillarity is a phenomenon of rise or fall of a liquid surface in a small tube relative to adjacent general level of a liquid when the tube is held vertically in the liquid. So what we have to do is, So take a small vertical liquid and some amount of liquid in it. So take this small glass with some amount of liquid in the glass and immerse it in beaker having the same liquid. So what will happen? There may be two conditions. The liquid in this small vertical glass may rise or it may fall. Okay, this is nothing but capillarity rise or capillarity fall. Let us see when it will rise and when it will fall. If you see, the rise of the liquid surface is known as capillarity rise, while the fall of the liquid surface is known as capillary depression or capillarity fall. Let us see the expression for capillarity rise. Fine. So if you had seen, there is a small glass tube. So to this, the surface tension will always act on the top layer. So if I had cut it and in a half part, so this is how my surface tension sigma will act, right? And if let h be the height of the liquid in the tube and sigma be the surface tension of the liquid and theta be the angle of contact between the liquid and the glass tube. So if you had seen the weight of the liquid in this height h, if I want to find weight of that, how to find weight? So as we know, density is equal to mass by volume and mass is equal to density into volume. So weight is equal to mass into gravity and mass is density into volume we can written as area into length into gravity. So weight is equal to density into area into length into gravity. So if you had seen density and gravity here and we have to write area and length. So area of the tube into height h is the length here. So area of the tube is 5/4 d square into h into rho g. So this is the weight of the liquid having in the vertical tube. So we will equate the weight of the liquid to the surface tension force, and the surface tension force is acting on the circumference of the top layer in the vertical tube. So it is nothing but sigma into circumference into cos theta. Why? Because of my liquid layer is making an angle theta with respect to vertical direction. So this is my liquid layer and this is how the surface tension sigma is there. It is making an angle theta with vertical. Okay, so if I resolve it, I will get this as sigma cos theta. Fine. So sigma cos theta into the circumference is pi d. So this is the surface tension force. So the surface tension force just we had obtained equated to weight of the liquid in that column. We will get the equation for h. That is pi/4 d square into h into rho g is equal to sigma pi d cos theta. If we solve for h, we get h as 4 sigma cos theta by rho g d. This is the expression for capillary rise or capillary fall. Okay. Next, whenever we had taken water, so water will have an angle theta 0. If substitute the theta 0 in the same equation, we will get h is equal to 4 sigma by rho g d. Let us see the same expression for fall also. So we will get the same expression for fall, but while rising, the top layer looks in this shape, while falling, the top layer will look like this shape. So we will obtain the same equation for capillary rise and capillary fall also. Let us see what is vapor pressure and what is cavitation. Fine. So vapor pressure, to define vapor pressure, let us take a small beaker with liquid filled with only some part. The entire part is free. Okay. So what will happen? During some time, evaporation will take place. So all these vapors will produce here. Okay. How this evaporation is taking place? So during vaporization, the molecules will escape from the liquid layer. Okay. So all these accumulated vapors will exert some force on the top layer of the liquid. So that force, the force produced by these vapors is known as vapor pressure. Next, what is cavitation? So cavitation means consider a pipe in which water molecules are flowing. So for example, in a condition, if the pressure of the water molecules flowing in the pipe has decreased to less than vapor pressure, then what will happen? So these molecules will further vaporize. These liquid molecules will get vaporized. So these molecules, as these are vaporizing in a low pressure region. Why you are saying low pressure region? Because there in that region the pressure is less than vapor pressure, and these molecules will go to the high pressure region and they will burst with high energy there. That is known as cavitation. So if you see here, the cavitation is the phenomena of formation of vapor bubbles of a flowing liquid in a region where the pressure of the liquid falls below the vapor pressure, and they will sudden collapse of these vapor bubbles in a region of high pressure. Such as this phenomenon is known as cavitation, right? As these vapor molecules are collapsing in high pressure region, so they will impact very high energy on the walls of the pipe or any container. So we have to avoid that condition. We will see in detail about this cavitation while we are discussing flow through pipes. The next is compressibility. So compressibility is the reciprocal of bulk modulus of elasticity, where we denote bulk modulus of elasticity with symbol K. Let us see what is bulk modulus. So bulk modulus is defined as the ratio of change in pressure to the volumetric strain. Let us take a cylinder having a piston inside it. So, and let us see this piston inside the cylinder, some gas is filled. Now move this piston towards the left side, that is, let us compress it. So what will happen? The pressure, we are doing compression, pressure will increase from P to some P plus dP. As we are compressing, volume will decrease from V to V minus dV. So the change in pressure is P plus dP minus P. So change in pressure is dP. Similarly, the change in volume will be dV. So volumetric strain for a decrease in volume will be change in volume, which is minus dV, to the initial volume. This is my volumetric strain. So bulk modulus is the ratio of increase in pressure to the volumetric strain. So the increase in pressure is dP by volumetric strain, which is minus dV by V. If I rewrite this equation, I will get it as minus dP into V by dV. So this is about your bulk modulus. So what is compressibility? Compressibility is just inverse of bulk modulus. That is volumetric. Compressibility is defined as ratio of volumetric strain to the increase in pressure. Okay. So this is about compressibility. Thank you.